Okay, I wanted to produce a video on work and energy, and this is a very fundamental topic in physics and one I wish I would have been able to talk about more before I left, but we'll talk about it a little bit more on Monday. But the basic idea behind work is that work is what you do to an object, and when you do that, you increase the object's energy. We have two types of energy. We talked about potential energy and kinetic energy. But basically, when you do work, you apply a force on an object over a distance d. And if both the force and the distance are lying in the same direction, you can simply multiply the two numbers and you get the amount of work you did. But it's critical that force and distance for this equation are in the same direction. I should say force and displacement would really be Fx. But I think you get the idea. To be in the same direction. If that's the case, then you can simply multiply them. If it's not the case, in other words, if the force were like this and the object happened to be moving at some angle like that, then the amount of work done is equal to the force times, and if this is an angle theta here, be force times distance times the cosine of that angle theta. So really, if you're pushing an object, you want the object to move in the direction you're pushing it in order to get the maximum work to the object to increase its energy. Okay, so that's just something to keep in mind. And you may wonder, when wouldn't you be pushing in the same direction that the object moves? Well, I'll give you a few examples where you'll see in just a moment. So one place where we can apply this equation then is we can take work equals force times distance. And the force, let's just take that to be the force due to gravity, which is equal to the object's mass times gravity. And let's say the distance here is the height that you're moving the object up. We'll call that the distance. All right? Or I'll call it the height. We're moving the object up a certain distance. So if the object's here and it has a mass m, and then you lift it up with some effort to here, it still has the same mass, and that distance is h, then the work done is simply the force, which is this, times the distance h. So work done is equal to mass times gravity times height to get the object from this level to that level. Okay? So the same would be true, now to get back to the thing we just asked about. If, let's say, I am pushing the object up a ramp. We just spent a lot of time talking about a ramp. And the object's initially here and the ramp has a height h. And I push the object to the top of the ramp like this. Well, at the top of the ramp, the object's height is h, but I moved the ramp. Let's call this angle here, let's just say it's 30 degrees. I moved this object up this distance here, so the distance I moved the object is this distance. But the force that I applied, well, you could say the force that I applied is in this direction also. But we typically, when we're dealing with gravity, we like to use the force due to gravity. And if we're pushing against the force due to gravity, that implies that we're pushing the object up that way. So what I can't do in this situation is I can't say, oh, the total work done here is equal to the force due to gravity times this distance here. That would give me more work than I actually did to push the object up. Because in truth, the amount of work I did is equal to the force due to gravity times this height here that I moved the object, mgh. So in other words, whether I move the object up the ramp like this, here, or whether I just lifted the object from the ground up a height h to reach its top right there, in both cases I applied m times g times h. And I'm going to show that to you right now. So let's say I'm pushing the object up the ramp here. This force, how much force does it take to push the object up the ramp? Well, in lab 8, I think, you found that the amount of force that it took to keep an object on its position on the ramp, force is equal to m times g times sine of theta. Many of you got that graph where you saw a graph that looks something like this, and some of you did identify this if this is the force and this is the angle. Some of you did identify the shape from the lab as looking like a sine curve. It's the amount of force it took to keep a block in place on a ramp. As you increase the angle, it takes more force. And it maximizes at 90 degrees, because at 90 degrees this thing is 1, and it's just equal to the weight of the object. So here, this force then is mg times the sine of the angle. All right, so what's the height here? This height is h. So you could say, or I could say that the work required here, work required is force times distance. I'll turn red here so that you can see it more easily. That force is equal to mg sine theta, and multiply that times d, and that will give you the work it took to get the block from here up the ramp to here. Well, what is d equal to in terms of h? Well, h is equal to what I wrote here is d times or divided by the sine of the angle. And how do I know that? Well, I know that. Whoops! Erase that. I made a mistake. None of you caught me. Oh, that's right. You can't catch me because I'm on video. H here is equal to d sine theta. That's SOHCAHTOA. So therefore, d is equal to h divided by sine theta. Alright, so if I take this d here and replace it with h over sine theta, I'm going to have to go to another slide. I wrote that, just checking what I wrote on the previous slide here. Okay. I would find, I'll rewrite what I just wrote. I wrote that W equals mg times the sine of theta times d, but d is equal to h over sine theta, where, just to remind you, this is h, this is d, this is theta. So if I plug this into here, what am I going to get out? I get out the amount of work it takes to push the block up the ramp is equal to mg sine theta times h over sine theta. I cancel the sine thetas, and I'm back to mgh, which is the same amount of work it took to simply lift the object up from here to here. Okay? We're going to use that in a future video. That's enough for this video.